of these diagnostics is largely to make it easier to perform binary neutron star simulations with Illinois GRMHD. And without too much trouble, GR Hydro and any other hydro-based compatible GRMHD thorns in the Einstein Toolkit. So I wanted to go a little bit over some of the difficulties in solving the GRMHD equations numerically. In multi-messenger astrophysics, the context is simple. We want to model strong, rapidly changing gravitational field astrophysical phenomena. It would be amazing if we could reproduce a short GRB. I think we're a long ways off from doing that in a self-consistent fashion. I don't think there's much debate about that. Circumbinary disks is another possibility, and there are many, many more, black hole neutron star, etc. The first difficulty, disparate length and time scales. We have to resolve features at the level of black hole horizons. Obviously, magnetic turbulence, MHD turbulence, is an extremely difficult thing to resolve, and one major issue is it occurs over large length scales. Small scale turbulence over large length scales means tons of resolution, the largest supercomputing simulations ever performed in numerical relativity, which David mentioned during his previous talk, during this past, the talk before mine. Were from the Kyoto group, those were the most expensive numerical relativity simulations ever performed. Obviously, and then going to the largest scales, we need to resolve the gravitational waves. So back out in the gravitational wave zone, where we have waves length scale m, which, or of order 10m, which can be of order 10 to the 3 times the strong field. And then that's not to mention the fact that we need to push the outer boundaries far away, because we don't really have good boundary conditions for general relativity at finite distance. So there are some solutions to this. You can use non-uniform numerical grids like AMR. You can develop codes for massively parallel HPC simulations, and then you can just sit down and wait while the computers crunch and your simulation results come in. I think there are some new solutions that are some new ideas for handling some of the major difficulties of binary neutron star simulations. We can cheat in modeling neutrino physics, photon physics a little bit. The question is, how much do you want to cheat? And that's the sort of indirect proportion to how cheap you want your simulation. The more you cheat, the cheaper your simulation becomes, and the less physically reliable it becomes. There are lots of ideas for handling MHD turbines. Of course, David's idea is pretty new. It raises additional questions, as would any other method that doesn't exactly try and resolve these MHD turbines at very, very small length scales. Another idea that has recently come about is to use, basically do some shearing box simulations, apply some deep learning algorithms to learn basically how very large, basically over larger length scales, how small scales turbulence can affect those larger length scales. I think it's a cute idea, and the lovely thing is you can validate it against new shearing box simulations. So here is the most popular method in numerical relativity for handling these disparate length scales with numerical gridding. I presented an alternative approach yesterday during my own talk that takes advantage of near symmetries in binary problems. We have basically a spherical grid centered here and another spherical grid centered here with a logarithmic radial coordinate moving out. Now what's lovely about that is after merger, if you perform a binary neutron star simulation, the fluid elements largely track coordinate lines. And that means that you lose angular momentum at a much, much lower rate than you would if, say, you performed it on a Cartesian. That's a very, very much a work in progress. Second difficulty, you have to worry about the divergence of the magnetic field. Mark yesterday gave a very nice talk on this, and a clever new approach that's not even listed here for mitigating the effect of introduction of divergences in your MHD simulations. So some popular solutions, you can use special finite differencing techniques, so-called flux-CD schemes, CT, CD. You can, and of course that enables the divergence of B to remain the same to the initial value, to round off error at all times. Later on in the simulation, there's hyperbolic convergence, meaning the approach that we took in Illinois GMHD to make it very easy to handle AMR refinement boundaries is to use vector potential. And so that's difficulty 3. When you have AMR, it makes it difficult. Certain approaches like flux-CT and flux-CD don't just naturally extend to the interpolation algorithms that you need for AMR. So you need to interpolate quantities at the boundaries. Interpolation errors will lead to monopoles, and those will grow over time. So how do you interpolate? Well, you can still, hyperbolic divergence cleaning still allows for that. But in my experience, hyperbolic divergence cleaning does not sweep away the divergence fast enough when we're talking about large amounts of matter crossing refinement boundaries continuously. It just can't sweep it away fast enough. Now, that statement changes if you have a neutron star that's stuck in a single refinement box for all time. Hyperbolic divergence cleaning works actually relatively well in that case. So you can also use special interpolation operators to effectively maintain that lovely algorithm of flux-CT or flux-CD at refinement boundaries, and there's a scheme authored by Balsara to that effect. And of course, the approach that we decided on in Illinois GMHD was a vector potential instead, so that any interpolation scheme will ensure and guarantee that divergence of the magnetic field remains 0 at all times. There are strong shocks, so in these simulations, right? The surface of the neutron star is a wonderful case in point, or an insidious case in point, however you like to look at it. Orders of magnitude drop in density to atmosphere levels over the span of a single grid point. We need a high-resolution shock capturing scheme to handle this sort of thing. It requires that you write your GMHD equations in a conservative form. Oh, interesting. I think I put this in a lecture at one time. Algorithmic ingredients. Here's some of the basic algorithmic ingredients. I don't want to go over this in too much depth. Just to say that these are sort of the basic ingredients you're going to have if you want a GMHD solver. You're going to need a reconstruction scheme, Riemann solver, conservative and primitive solver. Each one of these algorithms, I think especially conservative and primitive, is very difficult to get right and do well. So there's GMHD flows into black holes. Well, you can always excise GMHD data deep inside a black hole. You can be fickle, and just talk to anyone who's dealt with that and excision, who needs to use excision, like the folks who do generalized harmonic formulation simulations. It becomes a control theory problem. Gauged characteristic modes can be superluminal, so if B significantly contributes to T mu and it's sharp, you can get crashes. Boy, I've seen those. You can check conservative. So here's the approach that's used in Illinois GMHD to help with this. You can check the conservative variables prior to converting to primitive variables, and then move those conservative variables to a physically valid range prior to the conservative to primitive solve. And it turned out to be pretty robust, especially when we talk about black hole, interior black hole horizons. Another approach that I find quite useful is to just put a cap on the density inside the horizon so it doesn't get too out of hand. And that's what I say here. Difficulty number 6, as if this weren't difficult enough. Regions where the magnetic field dominates the dynamics, like in neutron star and black hole magnetospheres, basically results in the GMHD equations effectively becoming stiff. If you look at the T mu nu, you'll see quantities like P plus B squared over 2. Well, if B squared over 2 is orders of magnitude above P, well, the truncation errors in B squared over 2 can be of order P. And what that means is your primitive to, your conservative to primitive inversion can be extremely, extremely difficult to get right. And so effectively, there are some solutions to handling this. You can set a density floor in your atmosphere, or you can set PV or P-gas is some large but trustworthy value and low-density regions. But still, with GRMHD, it's going to be an ideal GRMHD, but this is going to be a tough proposition to get right, a tough challenge to get right. So what I've done, partly in response to this, is develop a GRFFE code, which solves the equations in the limit where P goes to 0, basically. One idea is one could map between these two codes, or switch between these two codes depending on whether you are in a highly magnetized atmosphere or not in a given simulation. It's a tough prospect because it's a one-way membrane of information from GRMHD to GRFFE, but you can't go back. GRFFE tells you nothing about the fluid data. It tells you nothing about the P's, the rhos, the H's. So I thought this was really cute. I went back and I found an old talk on Illinois GRMHD, and this is a slide. Oh, it's such a cool thing, right? A slide from August 2015. We all know what happened in September 2015. I gave this talk and I had this slide. Anyway, so cool, right? The idea was, we thought even at that point that advanced LIGO would be primarily a binary neutron star detecting machine. And it turns out it's mostly a binary black hole detecting machine, but also we detected a couple of binary neutron stars, knock on wood, for that second guy. But the idea was, of course, we still knew that we're going to have very poor gravitational wave source localization. So you only need an electromagnetic counterpart to pinpoint the gravitational wave source. So then the question is, what sort of counterpart should we look for? What sort of insights might the counterpart yield? And to fully answer these questions requires dynamical space-time GRMHD models. That's the motivation for Illinois GRMHD. That's the motivation for us talking so much about about GRMHD in general at this workshop. So basically said all that. So problems, what to look for, how to gain insights, right? We put our governments in the countries from which we originate spend billions of dollars on state-of-the-art telescopes, state-of-the-art gravitational wave interferometers. It's our job as the folks who do the simulations to make sure and maximize their bang per unit buck, or whatever, okay? So it's highly, highly motivating, and I think now is the time for us to bang the doors of our funding agencies and say, hey, it's the age of multi-message astrophysics is upon us, at least gravitational wave anchored multi-message astrophysics. We're going to need to increase our numbers greatly, first of all, and second, the funding is going to have to increase in proportion to that. So I hope you'll hear the rallying cry and write your congressperson or government official to make that message clear. What's that? Okay. Come on, people. Everyone who's listening, write your congressperson. We need support for this sort of science to maximize the science we get out of these hard-fought observations. Sorry, that's just how it is. This is a schematic. This is an actual result from a circumbinary disk simulation where we track magnetic field geometry. This uses the same code as Illinois GRMHD, rounded off error green. So here's where I would normally talk about motivations for why we wrote Illinois GRMHD, but I'll spare you the detail. It's a very entertaining few slides, as you'll see as I flip through them. The good, the bad, and the ugly. Poor Tuco with the rope around his neck. I'm tired as, I'm mad as heck, and I'm not going to take it anymore kind of stuff. At some point, you just decide you got to rewrite the code. It's no longer maintainable, and that's what Illinois GRMHD was written. The sort of feelings that led to Illinois GRMHD being written went from about 70,000 lines of code to 2,900, keeping only the core robust features that we've been using in the past decade for all of our GRMHD simulations when I was in the Illinois group. And now, actually, I want to go over a little bit on how you can use Illinois GRMHD for binary neutron simulation. It's been a long time coming. I've sort of put this off long enough, so I figured I'd go through a parameter file that's publicly available here. So just download an Einstein Toolkit, a 2019-03 or later release, and you'll find when you download it in this directory, this file right here, which is mag nsnstest.par. So from this, and this will serve as documentation for the future generations as well. From this, you can start a magnetized binary neutron star simulation with Illinois GRMHD. And I just want to go over some of the new stuff that W.B. Thorne's diagnostics provides. Basically, it was the missing link. It fills in the gap that was in the toolkit for really making it possible to do binary neutron star simulations with Illinois GRMHD. So first, there's the C magnetic fields BNS module that seeds a poloidal magnetic field in each neutron star. What you do is you iterate to figure out the parameters that you need. You have to first convert your dimensionless units to some degree to well, the G equals C equals 1, our God-given units, to something more physical. You assume a neutron star has 1.4 solar mass. You basically assume a mass for the neutron star if you're using a very simple equation of state, or you just know it from your more advanced equation of state. You measure the maximum d squared, and that's going according to the prescription that we use for our poloidal magnetic field. That's going to also appear in the same place where the pressure is maximized. So you look at b squared over 2p. That ratio corresponds to a physical magnetic field strength, 10 to the 15 Gauss in this case. And that's how you do it. So you set it using this Thorne, which is in W. Thorne's diagnostics, which computes little b squared by itself. And p, of course, is just a native variable of Illinois GRMHD. And you use simple AMR reduction operations to compute the maxima, which is lower in this parameter file. So look for the word reduction if you want to see how to do this thing. They're particle tracers. So this is actually a very nice feature for visualizing magnetic field dynamics. So in the GRMHD limit, magnetic fields remain attached to the fluid elements they thread, with the exception of magnetic reconnection, which is should be a rarity in your GRMHD simulations. So the frozen-in condition ensures that the magnetic fields remain attached to these fluids. So the idea is very simple. Atop your normal space-time evolution, which it takes really small time steps because you're trying to model very sharp gravitational fields, you do an RK method that's updated every full eight time steps of your simulation. You have an RK method that tracks particles. So it solves the ODE, very simple ODE. dxi dt is equal to vi. And so you set an initial x, and it will xi, and it will track the particle as it goes, as it's carried along with the GRMHD flow. And this is very useful. If you don't do this sort of tracking of particles, when you try and look at your magnetic field structure in a movie, let's say you pick a given point to strike your magnetic field structure, you'll get what we call lightning bolts. Magnetic field lines, which are just streamlines of the magnetic field, of course, will appear, and then they'll take a certain characteristic, and then they'll change, and they'll go up, and they'll go haywire. Whereas if you use a consistent particle attached to a fluid element throughout the entire simulation, you can actually, in a faithful way, monitor how the magnetic field dynamics in the GRMHD flows behave. And so it's very useful. So you can see, for example, we've seen using this sort of approach, the twisting of magnetic field lines around black holes. If you start a torus around a single black hole, you'll actually see the magnetic field lines getting twisted up. You will see the Blanford-Zanaev effect take hold in real time in your visualization. It's gorgeous. So name of data file containing the Lorraine initial data, we call it resu.d. So this is a data file containing spectral coefficients. You can either download this from the Lorraine website, their FTP server, if you can believe those still exist, and they do, or generate it. And in fact, I think Josh is going to have a very nice catalog. He's working on a big catalog of binary neutron star initial data, a new catalog, built using Loran. So stay tuned for that exciting development. The next part of our parameter file is volume integrals GRMHD. So what I did was I wrote a volume integrals module that allows you to, in your parameter file, guide where the integration region is. And it can handle arbitrary, what I call Swiss cheese-like topologies. So basically, you can do a volume integral within a big sphere, and within that, you can excise some center region or any offset region. You specify everything in your parameter file. So this is a very simple example. So you can, by the way, you specify the integrand, and it's very easily extensible to additional integrands. So integrand of 1, just to make sure that the volume that we're covering gives you an idea of sort of the core sort of truncation error in your volume integrand. Setting the integral to 1 and seeing how close that is to the actual, say, 4/3 pi r cubed volume that you get in a given spherical region, for example. There's a center of mass integrand and a rest mass integrand. So center of mass, of course, does what you would hope it would. And it even gives you an option to say, okay, well, whatever you get as a result of that integral, set the AMR box to be centered at that. So, for example, right, the center of mass, you really prefer, when you're doing a binary neutron star simulation, that your AMR boxes are centered at the center of masses of each neutron star. So you basically pick a spherical region. You pick a spherical region within which you perform the center of mass integral, and it will track that as the neutron stars orbit one another. And that's how we track neutron stars in our simulations. And at the same time, we can do a lot of other cool diagnostic integrals, like track the total rest mass on the grid, track the total rest mass in whatever Swiss cheese-like volume we like. And finally, this is volume integrals vacuum. It's the same as this volume integrals GRMHD, but it doesn't depend on hydrolinks. So you can do this even in just a vacuum simulation. So you can monitor quantities like the Hamiltonian limit constraints, compute the L2 norms, and there's this neat thing to use previous integrands. So if you want to take a big volume and sort of shrink it down, or just look at big or thick spherical shells, this is a great way of doing that. So this is actually a more complicated set of topologies here, but you can find it in this parameter file right here. It's a slightly different parameter file. Note that. But yeah, if you want to add integrands, they're easily extensible. There's some ongoing work. Part of this has to do with PTCAN, which we're sort of transitioning to workshop today. Illinois GRMHD. So this is a sort of difficult decision to make. Should I keep Illinois GRMHD untouched in the toolkit and then develop my own extended GRMHD code? I like animals, so giraffe was GRFFE, my GRFFE code. I thought, why not walrus, right? Walrus, as we all know, walri have no divergence, right? So I'm just throwing it out. So I really do want to keep it untouched. It's sort of a pedagogical tool, and to be honest, in its name is encoded the fact that it's in round-off level agreement with the original GRMHD code of the Illinois group. When I develop a new code, it may have additional features, and who knows, it may break that by virtue of the fact that we want to choose a better default for our algorithms. We want to add better EOS support. Maybe some hooks to EOS Omni instead of the built-in simply polytrope. Try out some new, there's some very nice new off-the-shelf conservative primitive schemes. But I would like to incorporate some of these pre-conserved C2P checks and fixes that we currently have in our GRMHD. And I do want to continue what I've started with NERPI, and that's what I talked about yesterday. This code generation package where you Einstein's equations, you type them in Einstein notation, and their output is highly optimized C code. This is great for expediting the generation of new codes and new pieces of codes in existing GR infrastructures. And maybe add some MP5 for a new reconstruction scheme or a Wino, something like that. But all these are open source. I don't intend, they're open source in the sense that they're available already. I don't intend to reinvent the wheel. I intend to take another code and import it into my own. They will be assimilated. Resistance is futile, as they say. All right, so I just wanted to end my talk by showing you a recent binary neutron star merger simulation performed by Illinois GMHD. This is hot off the supercomputer. So here we have the formation. You saw a couple orbits before the formation of this hypermassive neutron star. We got a lot of time now to talk because this hypermassive neutron star is one of the most stubborn guys I've ever had to deal with when doing these simulations. But I had more time now. It went through about 10 oscillations before it finally collapsed to a black hole. When it did, the black hole did not have too much of the drift. This is something that we've been looking at. If you look closely. Oh, it's probably, I have the frame rate really high. That's what's going on. Yeah. Yeah. There it does a black hole formation. Beautiful. And you can see the black hole. It's going to start evacuating the ISCO region here in a second. But this is the time. It's about 57, 58 milliseconds. This is another. This sort of harkens back to one of my very first slides, which was the very disparate length and time scales that we have to deal with in numerical relativity simulations. GRBs are generally things that last on a time scale of seconds, and short GRBs, on time scales of tenths of seconds on average. This simulation in total lasted of order 100 milliseconds, something like that. While at the end of the simulation, there was an accretion disk around the black hole. It was bigger than you saw, than you could see there in this box. But long-term simulations with full physics, including photon transport, neutrino transport, as realistic equation of state you can possibly muster, full realization of full modeling of the magnetic field dynamics, the GRMHD turbulence. These are going to be required elements to doing this right over long length scales, over long time scales. And I would argue that the only way we're going to be able to do it right over time scales of order of a second or two is to move beyond Cartesian grids over long-term simulations. There's just no way we can maintain sufficient angular momentum conservation over the long time scales necessary to reproduce the necessary physics that come after the multi-messenger component, the non-gravitational wave component to these simulations, unless we move to very new algorithms, new approaches, and add a lot more physics and necessarily expense to these simulations. So write your congressperson, do invest efforts if you have efforts available to add to completing these goals, because it's the only way we're going to make a really compelling case for our field. Thanks.